Hello and welcome. Contour integration today. We're going to be dealing with the integral of the square root of x over 1 plus x cubed between 0 and infinity. Okay, let's jump straight into it. We've done quite a few of those now. So we're going to consider, of course, a complex function f of z, and this is going to be the square root of z over 1 plus z cubed dz over some sensible contour gamma, which we're gonna talk about in a minute. Well, first of all, let's look at this particular square root of z. Whenever we have fractional powers or logs, we're gonna have branch points and branch cuts. So we have a branch point at z is equal to 0. That's because it's the square root of z, so that's 0 there. Of course, if we had the square root of z, I don't know, minus 2, the branch point would have been at z is equal to 2 and so on. So what that means, let me just draw here the complex plane. It means here we're going to have a branch point, nothing to do with poles at the moment. Okay, so that means we have to cut the plane from this branch point to away from it to infinity at some point. So it's like we're going to create like a spiral staircase. So usually we're going to take the branch point, sorry, the branch cut now along the coordinate axis somewhere, but we can actually take it at any arbitrary direction. For example, let's have a little think about what kind of contour we'll do for something like this. Okay, first of all, we can consider to take the branch cut perhaps, well, we can't do it on the negative x-axis. Why is that? It's because we already have a pole in there, okay, because z cubed plus 1 is equal to 0. Z cubed is equal to minus 1, so we're going to have, of course, minus 1, and we're going to have also 1 at 180 divided by 3 at 60, and another one symmetrically conjugate down there. So because of the pole here, let's actually mark the pole because this is not going to go away. One of them is at minus 1. Since we're discussing this, we might as well just get the other 3, not the other 3, the other 2 rather. I hope you can see by inspection there's going to be 1 up here, that's at e to the I pi over 3. And this one, I'm not quite sure what argument I'm going to write. Let's write it for the time being as e to the I 5 pi over 3, or you can think of it as e to the minus I pi over 3. The reason I'm not quite sure what argument I will put there is because I don't know where I'm going to take my branch cut. So this is now the 3 poles of this particular f of z. We cannot take the branch cut along the negative x-axis because of this pole here. Where can we actually take it? We can take it on the positive x-axis, and I think actually I didn't prepare actually for that very well. I think this particular contour, I'm not going to do it like this. If we need to indent the origin, something like that. And if we were to take a contour which is like a sector, and in order, because we've got z cubed, so e to the, it's going to be 120 degrees here, so something like that. Okay, so this is going to be radius r and epsilon here, this angle being 120 degrees or 2 pi over 3. I think, and we trace of course the contour like this. Where we're going to take the branch cut if that's the case? Well, if we have something like this, we can take it in any arbitrary direction, in which case these poles will not even matter. We can actually throw them away, and we're going to have just this one inside this curve. I think you can actually try it yourself and see if this particular contour will work. I've got a feeling we will work without any problems. But for today, the contour that we're going to use, I'm going to play safe. I'm not in any mood to improvise. So we're going to use the keyhole contour and a keyhole to the right. So what that means is this is our branch point because of the square root. This is our pole at -1. And I'm going to indent the origin. I'm going to take my branch cut, indicated by this curly line on the positive x-axis, and I'm going to go just above and just below the x-axis, and then a radius sufficiently large to include all my poles. Annoyingly, I'm going to have all 3 poles inside my gamma. So this is e to the I pi over 360 plus 120 plus 120. So it's going to be e to the I 5 pi over 3. The argument now will go from 0 to 2 pi as I've just done it in there. The radius of the small circle, epsilon as per usual. Radius of the big r, again as per usual. The whole curve is going to be denoted by gamma. So that's my gamma. And for simplicity, let me indicate this as my gamma 1 and the inner one, the inner circle, as gamma 2. Okay, residue time. And that is not going to be very nice. I think a lot of the time will be wasted in calculating residues for this particular one. My choice of gamma here is not the best. Maybe I should have improvised and go for that slice, because at least it would have been just a single pole to consider. But let's go for it. And let's hope we don't make mistakes here. So the first one is the residue of f at, let's do the one at -1 first, because it appears to be easier. So it's going to be the limit as z tends to -1, z plus 1, and then we have, of course, our f of z multiplied by the f of z. Let's jump straight onto it. So that's going to be the square root of z over 1 plus z cubed. I can use L'Hopital's because I can treat that as being a numerator, so it's a 0 over 0 case, but this does factorize. So I'm going to go for the factorization of this sum of cubes. So that's going to be the limit as z tends to -1, square root of z, bracket, z plus 1, and this now will factorize sum of cubes, z plus 1, and then it's going to be z squared minus z plus 1. So this will now cancel. So we're letting that go to -1. So that is the square root of -1 going in there. So that square root of -1 is the principal value. Of course, we need I. And then we got -1 all squared, which is going to be 1, minus -1, which is +1, plus 1. So I got 1/3 of I. Let's write this, because I'm going to need a lot of board space, I guess, for this one. Let's write all these residues on the right somewhere. So that's the first one, so we don't lose them. And let's jump to find now the residue of the pole there. So a little bit tedious, this part. I hadn't really accounted for that when I made the choice for this particular gamma, but I'm too scared to go for the slice, I have to be honest with you, for that 2 pi over 3 slice. So that's this one now. So the residue of f at e to the I pi over 3 is the limit as z tends to e to the I pi over 3. And now z minus e to the I pi over 3 times my f of z. And my f of z is, of course, this. I'm going to write it on the top as root z, or actually I'm going to write it as z to the half, because I think I'm going to use L'Hopital's for this one. And on the bottom I've got 1 plus z cubed. So of course this particular quantity, this particular limit, as per usual, it's a 0 over 0. So rather than factorizing and cancelling a bracket, it's not that difficult. I can't do it like I've done on the previous one, because of course it's going to be, of course, there a z plus 1, a z, oops, hope you can see it. It's not that difficult to factorize this. Z minus e to the I pi over 3, which of course will cancel that bracket, and the other one will be z minus e to the I 5 pi over 3. And then just putting obviously that in there and in there, but I don't fancy the tidy up afterwards. So let's use L'Hopital's rule here. So differentiate top and bottom separately. So let's write the limit first of all. Okay, differentiate this quantity with respect to z is just 1 times the square root. Okay, and then differentiate the square root, so that's going to give us a half z to the power of minus a half, that's this bit here, times this bracket unchanged, but this bracket will die because of course the limit will kill it. And on the denominator we got 3z squared. So that when it goes into this bracket, this will be gone. I'm going to take the limit. So I'm going to have in there e to the I pi over 3 all to the half. So it's going to be e to the I pi over 6. Okay. And then I'm going to have on the denominator 3e squaring now e to the I pi over 3 is e to the I 2 pi over 3. Okay. That's definitely a third, first of all. And this is now 30 degrees minus 120 degrees. So that is, of course, minus 90 degrees. So that's e to the minus I pi over 2. Of course, one could argue and say, look, you're not allowed to have this kind of arguments because of the branch cut. So your argument will run from 0 to 2 pi. It hardly matters for this one. I'm a bit sloppy. I'm going to leave it like this. But if it makes you happier, okay, bang another 3 pi over, sorry, another 2 pi to that. And it's the same as, of course, e to the 3 pi over 2i. It's just getting a number basically for it. It doesn't get affected by the branch cut. I hope you follow what I'm saying in there. So this one, or this one, is going to be a third. What is e to the I pi over 3? That is a minus I. So it's going to be a minus a third I. That's what I make this particular residue. So let's write it on the side here. So the second residue is minus a third I, and we got one more to work out. That's the one at e to the I 5 pi over 3. So let's doctor this a little bit. So residue of f at e to the I 5 pi over 3, e to the 5 pi over 3, 5 pi over 3, that's exactly the same. E to the 5 pi over 3 tends to, I would have used L'Hopital's again, differentiate top and bottom with respect to z. The differentiation, of course, is the same, but of course here, when I come to differentiate the z to the half, leave this bracket alone, that would have been to the 5 pi over 3, but it hardly matters because again it would have gone. So the only thing that will change when I try to calculate this residue is this very last line, the actual evaluation. So what do we get for that? We're putting e to the I 5 pi over 3 all to the half. So it's going to be e to the I 5 pi over 6 over 3. Squaring that is going to be e. 5 thirds times 2 is 10 thirds pi I. That has already a multiple of 2 pi in it. So let's get rid of it. So e to the I 5 pi over 6. I don't have a calculator. If you had a calculator, bang into a calculator, save yourself some time. 3, 10 thirds take away 6 thirds is 4 thirds. So that's 4 thirds pi I. And what happens with this one now? That is 150 minus, that's 150 degrees there, minus 4 thirds is 240. So it's going to be minus 90 on the top. So this is going to be equal to 1/3 again, e to the minus I pi over 2. Okay, which again, we had this on the previous one. Again, I can write it as e to the 3 pi over 2, so we can stick with the conventions of the argument in there, but it hardly matters for this evaluation. This residue is also 1/3 minus a third I. Of course, this is a third there, and this is a minus I. The position of that is down here somewhere. Okay, so far we got the 3 residues. So let's not lose them, and let's clear the board and let's start our work. It's going to be a detailed lecture. I'm going to put all the estimations in detail. I don't know how many of these estimations I've done by now. I might abbreviate very few things in the whole calculation. I'm trying to create lectures where it's evident to people that kind of like do not quite haven't quite grasped this in the lectures at university, how to do this. So the next step is to actually say, okay, if I integrate in sections around gamma 1, then from r to epsilon, then around gamma 2, and then I didn't put an arrow there and an arrow there, then of course by the residue theorem, in fact I would have written here this integral by the residue theorem, it's going to be 2 pi I times the sum of the residues of f inside gamma, and of course the sum of the three residues here is two of them will cancel out because the third minus a third will cancel. Let me just write them for completeness, just and then on the next line I'll throw them away. So minus a third I, so that's by the residue theorem. And if therefore I integrate around gamma 1 plus, I've gone round gamma 1 and then from r to epsilon, from r to epsilon plus around gamma 2 plus epsilon to r, f of z dz. The answer to that, of course, is going to be this. Let's put a curly bracket. Can't fit the curly bracket there. It's going to be super curly. There we go. And this, of course, these two things will cancel. What does that simplify to? We're going to have a minus here. So I times I is minus 1 times the minus a plus. So that gives us, in fact, 2 pi over 3. Okay, so if we integrate around the entire contour in an anti-clockwise direction, the answer to this complex integral is 2 pi over 3. I'm just going to grab it off from here and just write it there to just allow a bit of extra free space on the board. So this is now so far so good. This is my plan. Usual plan in this kind of things is, of course, my real integral will come out from the straight line sections once I let r go to infinity and epsilon shrink into 0. So first of all, I want to show that the contributions around gamma 1 as r tends to infinity and the contribution around the gamma 2 as epsilon goes to 0 have 0 contribution. They vanish in the limiting case, and I have to do these two bits first. After that, it's plain sailing. This is what takes quite a bit of time in general in this kind of work. So let's look first of all. We're going to start with the estimation around gamma 1. So the modulus of the integral around gamma 1 of f of z dz, we're going to parameterize it. Usual parameterization, but now we should really be experts. So around gamma 2, sorry, not gamma 2, gamma 1, my z is going to be r e to the I theta. My dz is going to be I r e to the I theta d theta. And my theta will run from 0 to 2 pi. 0 to 2 pi. So I'm going to put this inside my integral now. It's all parameterized, 0 to 2 pi. And we're having my square root of z. The square root of z is the square root of that. So it's going to be r to the half e to the half I theta. So that's the square root of z. 1 plus z cubed r cubed e to the 3I theta. 3I theta. And my d theta is going to be, let me just, it doesn't really matter, let's write it here. I r e to the I theta d theta. Any cancellations for that? Unfortunately not. It'd be nice if we could cancel something there, but unfortunately nothing cancels. So a little bit of a tidy before I go to my next line. So 0 to 2 pi, and I'm going to have on the numerator an I r to the power of 3 over 2, that r and that r, and the exponentials are going to be altogether similarly 3 over 2 I theta let's put the d theta at the end. The denominator, nothing to do really. I cubed e to the 3i theta. Close mod. No, oops, I'm outside the integral. Very bad of me. Close mod. Okay, so now we're going to use the standard inequality, which says the modulus of a definite integral is less or equal than the modulus of the integrand. So basically, we're going to move this inside in the integrand. We've done that quite a few times by now. Because unfortunately I do not record and upload at the same time, I don't know really what you have seen because I put things in all bizarre order for reasons I cannot really get into at the moment. So that is there in my d theta. Then of course I'm going to use the property z mod z of w is mod of z mod of w, and similarly that is the same as that. This works of course for complex or real numbers. So I don't want to waste a line in here. So first of all I'm saying is I'm going to put the moduli signs separately on the numerator and the denominator of this fraction. So that's this job done by using this particular one, and this particular one, I beg your pardon. And then if I have things that multiply, here I have 3. They, of course, this was for 2 or more. I'm going to put individual moduli. Let's actually use a red pen here so we can all see and be happy as to what I'm doing. And then I'm going to put individual moduli onto the top by using this one. 3. I cannot do it obviously on the denominator because of the plus that's connecting in there. Okay, what happens next? Just a bit of a tidy. So I'm going to go a little bit in detail on this estimation around gamma 1, and then on gamma 2 I'm going to have to rush, otherwise this lecture is going to get very, very long. So let's clear the board and let's see what we're getting. We are on a tidy up at the moment. What happened to my black pen? My black pen is down here. Okay, so this is less or equal from this line here. Okay, the modulus of I is of course 1. I lost there a 3/2 when I copied it. I do apologize, and I rubbed it off from there for you to have seen it. I'm very error prone. Please watch me, and I do apologize in advance. I should really start my lectures by apologizing for any mistakes that I'm likely or almost certainly going to do. Okay, this is now e to the I something real. This quantity is real with an I there, 3/2 theta. When you mod it, I have gone through this several times, the answer is 1. So the modulus of that is in fact 1. Okay, you can switch into sines and cosines and convince yourself that this is always 1 by using the identity cos squared theta plus sin squared theta is equal to 1. Now, this one, I cannot do anything at the moment, so let's leave it. I'm going to do an extra line just to show you what I'm going to do with this one. That's the denominator d theta. Okay, then we're going to use part of the triangle inequalities, beg your pardon, which says basically the mod of z plus w is greater or equal to the mod of z minus the mod of w. Okay, and one could argue that, of course, how do you know? Maybe this moduli is smaller than that, in which case that will not be true. But if that is the case, without losing any generality, I can just swap them around. So this is in fact greater than that, and this is positive. You can write, of course, or perhaps 0 if they're equal. That's the trivial case, I guess. Okay, but we don't want it to be 0 because of what I'm going to do next. So let's say this is in fact greater than 0. There's a positive answer between them. Okay, so if I flip it upside down, 1 over z plus w, therefore it be less or equal to the mod of z minus the mod of w. So I'm going to apply this to this denominator where this is my z and this is my w, or you can flip it. It doesn't really matter because there might be some technicality. Some people might argue if I write it as 1 minus, it hardly matters. So let's continue. Maybe you won't even notice what I was referring to. So now for this, going from there to there, less or equal, but this inequality, very important inequality. The top, of course, is unaffected. In fact, I could have put it outside the integral because the integral is with respect to theta and that's independent. And I can say now this is less or equal to the mod of 1 minus the mod of r cubed e to the 3I theta. I've just used this identity on the 1 over this. Okay, tidy. 0 to 2 pi r to the 3 over 2. Modulus of 1, quite stupid, I even wrote it, is 1 minus, now we have two moduli multiplied together. I can write it, of course, like this, like I did earlier on with the numerator. E to the I real, that has modulus 1. Let's cross it out. R is a positive quantity, does not even need modulus, so I'm going to squeeze the last line. Is 0 to 2 pi r to the 3 over 2 over 1 minus r cubed d theta. And the game is up now because, of course, if you see what happens, the integrand now is independent of theta. We can pull it outside all of this and integrate 1 d theta, and we're going to get another 2 pi. So we're going to get 3 over 2 over 1 minus r cubed integral 0 to 2 pi 1 d theta, which of course will now give us r to the 3 over 2 times the 2 pi, let's stick it at the front, 1 minus r cubed, which of course is of the order, if we look at what will happen, what is the, as we're going to let the r go to infinity, this is of the order r, this is insignificant, this is insignificant, so it's of the order r to the 3 over 2 over r cubed is 1 over r to the 3 over 2, and this, if we let r go to infinity, this tends to 0 as r tends to infinity. Okay, so what we've done so far, we've shown in the limiting case, as r tends to infinity, the contribution around gamma 1 of f of z is going to be 0. Okay, now for the second estimation, which is around the baby circle around gamma 2, as we let epsilon shrink to 0, I'm not going to be showing as many workings. I'm going to be speeding up a little bit. So this is now around gamma 2, and this is going to be equal to, parameterizing again. Let's have a look at the parameterization around gamma 2. Gamma 2 is a circle of radius epsilon, so the only thing that will change is the radius at the front. Epsilon e to the I theta. So dz will be I epsilon e to the I theta d theta. And the limits, because of the direction we're going now in a clockwise direction around that circle, it will not matter for the estimation. It's going to be 2 pi to 0 in that order. I'm going to leave this identity up there because I'm going to use it very quickly in this particular integral. So let's put our stuff in. So this 2 pi to 0. We got the square root of z. So that is going to be epsilon to the half e to the half I theta. On the denominator we have 1 plus z cubed, which is epsilon cubed. Looks very weird, epsilon cubed. Epsilon cubed e to the 3I theta, and my dz is going to be, how can I see it? Okay, I epsilon e to the I theta d theta. No cancellations taking place. Quick tidy, not doing anything really. This limits 2 pi to 0. I really don't like them. They're really getting on my nerves when I see them like this. I'm going to swap them. I'm not going to generate any minus signs because I'm inside the modulus still. I'll throw it away. Okay, it's a minus in there and then the modulus will kill it. So I'm going to swap them to 0 to 2 pi. They don't matter. So we're having an I epsilon to the 3 over 2. That's this 2 here. E to the 3 over 2 I theta over 1 plus epsilon cubed e to the 3I theta d theta. So is almost identical steps like the previous ones. I'm not going to be showing a lot of workings now. So what happens there? inequality number 1, this becomes less or equal, the modulus of the definite integral is less or equal than the modulus of its integrand. So this now, I'll move them inside the integrand. Boom. Then I'm going to use the modulus properties. Modulus of the top over modulus of the bottom. Okay, standard results. I don't want to be rewriting this just to do this particular line. Okay, so that's that. And then, because these are all multiplied, individual moduli on the top. And of course, for this, I will deal later with the triangle inequality that I've written down there with my black pen. All right, so what happens in there? Modulus of I is, of course, 1. Let's rub him off. Probably with my finger is better and quicker. Okay, e to the I something real has modulus 1. Goodbye, my friend. And epsilon is a positive quantity to the power of 3 over 2 is just simply epsilon to the 3 over 2. That's what survives on the top. Okay, what happens now with this? That's, I would have copied it again. And now maybe I can move this outside so we can see it better. This has no theta dependence, so we can write it as epsilon to the 3 over 2 and write, of course, a 1 on the top. So this is that. Okay, so now we have 1 over z plus w is less or equal, so let's write it here, epsilon to the 3 over 2, 0 to 2 pi is less or equal to mod of z minus the mod of w, mod of 1 minus the mod of epsilon cubed e to the 3I theta, mod d theta. Again, split into individual moduli here. E to the I real will be modulus 1. We've done it so many times now. And therefore, this particular quantity, I don't want to go any lower on the board. I'm just going to go back to the top, change that equal to less or equal because we have less or equal a couple of times. And that is going to be epsilon to the 3 over 2. I pulled it outside the integral. 0 to 2 pi. And I've got a 1 over modulus of 1 stupid minus epsilon cubed. That, of course, has modulus 1. And, of course, the theta. And I'm going to carry out this integration with respect to theta from 0 to 2 pi. These are all constants. Let's write them on the outside. 1 minus epsilon cubed, and I'm going to be left with 1 d theta from 0 to 2 pi, so let's stick a 2 pi at the front, and this is the answer for this particular one. What happens there now as we let epsilon this time go to 0? Okay, first of all, the dominant term in the denominator is the 1, so this will tend, the epsilon on the top, of course, will, if you let it go to 0, it will tend to 0 on the top, and the bottom will go over 1. This will just vanish really there. So it's going to be, of course, tends to 0 as epsilon goes to 0. And therefore, as we shrink this, the contribution of this integral vanishes. And therefore, we're now on the home straight, and we are going to get our real integral. We don't need any of this, so let's make some space. So let's write a line on the top as r tends to infinity and epsilon goes to 0. We're going to have the integral r is infinity to 0. Let's write f of z for the time being, dz plus the integral from 0 to infinity, and f of z again. We'll sort it out in a minute, the quantities. There's a little bit of work still to do. I forgot we have a branch cut there. Is equal to, we worked that out already from the residue theorem, is 2 pi over 3. So we have to be careful, because at first glance, when you're looking at this, if we were over the reals, and you would have said, well, if I swap these limits, these two things will cancel, and what is going on in there? It's not quite like that here. there's a little bit of subtlety. I've shown this before, so let's identify which one is which now out of those. I'm going to put a little identifier. The one that was going, the top one is the epsilon to r, so that's from 0 to infinity. This is the top section, and this is the bottom. So this is just up underneath the branch cut. This is just above. Okay, and I have said in the past, when we parameterizing along the positive x-axis and even on the negative, we're getting a little bit sloppy, and we say because we're on the x-axis, z is equal to x, we can just replace it with z is equal to x, and now the z will become dx. It's not quite true. Even on the negative axis is not quite true, but on the negative x-axis, the minuses sort themselves out and everything works. The reality, wherever you are on a straight line segment, your z is not simply x. It is actually, x is the modulus or parameter. You can treat it as a parameter, you could put t there, is e to the I theta. So if you're on the x-axis, on the positive x-axis, is that. If you're on the along a line, let's say along the y-axis, it'll be e to the I pi over 2, and so on. If you're there, should be I pi. And now on the top, let me just actually write it here. This is the top. Z is x e to the 0 I, while here on the bottom, your z is x e to the 2 pi I. The way we put the branch cut, the argument must run from 0 to 2 pi. So the argument there is 2 pi. Okay, let's differentiate. So that's going to be dx. That's a constant, of course, e to the 0 I. Same thing on this one. Dx e to the 2 pi I. And let's put now, I'm not going to be rubbing this off I've got up there. Let's put actually our f of z in each of those, and let's see what happens. Is equal to 2 pi over 3. And this is now square root of z over 1 plus z cubed, and square root of z over 1 plus z cubed. This and this. All right, now let's look at each of them individually as we put them in. What is e to the 0 I? E to the 0 I is of course 1, and therefore z is x. So if we, whether we put it now as z cubed, let's look at the z cubed here. Okay, z cubed, of course, I'm looking at this one here, is of course x e to the 0 I, or cubed, no problem. This will give us x cubed. That cubing it is still e to the 0 I. That was still gonna be x cubed. That is actually safe. Let's use a red pen for that, to replace it with z is equal to x. What about the square root of z? That is z to the half. I don't think will make any difference. X e to the 0 I all to the half is going to be x to the half, and of course e to the 0 I times a half is e to the 0 again, 0 I, and of course again is 1. So that's also safe. And the dz, of course, there's no substitution to do. The dz is equal to dx times 1. So that is also dx. So this particular integral, we can actually swap the x, so the z for x, no problem. This one is okay everywhere apart from this square root, as we will see. Let's check all these things. So I'm looking now at this and this parameterization. Z cubed, of course, is x e to the, what do we have in there, 2 pi I. And we need to cube it, of course. Okay, what will happen? Well, we're going to get x cubed. Okay, and then of course if we raise the exponential cubed, it's going to be 6 pi I. What is 6 pi I? Is the answer is 1, and therefore it's x cubed. Straight swap. Okay, the dz is there, is equal to dx. What is e to the 2 pi I is 1, so it's just basically dx. So we can swap this one. The difference, of course, in the square root. It's always on the square roots, cube roots, logs. You have to be very careful with these parameterizations. So we have now z to the half is equal to x e to the 2 pi I all to the power of a half. And now all of a sudden we have extra bits that got created. We go x to the half from there, and this bit here now becomes pi I. And so we have z to the half, the square root of z, is equal, what is that? Well, that's quite clearly -1. And therefore, this will swap for that. So this, we have to be very, very careful. So I'm going to leave that up there now, rub off these bits, and we are done, practically. Okay, so let's see what we're getting for this. This integral is the one that we said the only thing that's different is on the numerator. We have a minus x to the half. The rest we can safely replace them for x's. dx, and the limits, of course, infinity to 0. And this one is just a straight swap, 0 to infinity, and then we got x to the half 1 plus x cubed. Let me just wrap this off. That, of course, is equal to 2 pi over 3. I don't want to waste a line, and of course I got a minus in there, so the minus will be disappearing, and I'll be swapping the limits. So that's now exactly the same integral that appears twice. And of course, the next thing that I'm going to do, I'm going to put a 2 at the front here and lose him. And the last thing, which I'm not going to bother, is now to lose the 2 and lose the 2 here. And therefore, I hope I've done it correctly. The answer to that is pi over 3. Okay, quite an intense integral done by complex methods. And if you remember what happened in the beginning when I showed you the indented slice, don't know if you remember it, this contour here, I think this will also work. It's going to have less work with the residues. I think the approximations or the estimations, shall I say, will be exactly the same. You just have to be very careful with parameterizing this bit here, and you'll be done. I think you'll get exactly the same answer. I hope you enjoyed it. I hope you followed it. Who's laughing now?